Alright, hello you guys. We are going to look at our non-parametric assignment this week, and I've already downloaded the week 6 zip file and unpacked it, and I'm going to get in there and click on the week 6 our project file to open that up in our studio. And if our notebook doesn't open automatically, you should be able to click on the week 6 our notebook.rmd file and it should open. But mine is already open, so I'm going to go up to the top here. And this week you were reading about non-parametric tests, and just like parametric tests, there are a number of different non-parametric tests. And last week you saw there was a non-parametric test for an independent t-test, and that was the Mann-Whitney U. And there was also a non-parametric equivalent for the paired t-test, and that was a Wilcoxon-signed ranks. This week, rather than have you run a bunch of different non-parametric tests, I am focusing on the chi-square goodness of fit and the chi-square test of independence, or also known as the chi-square test of association. And these chi-square tests were not the focus so much in the field text, but I wanted you to see these two tests, the chi-square test of independence or chi-square test of association specifically gets used quite a bit because these tests are good for looking at categorical data, and so there's often a good bit of that. So that test gets used a bit. So I wanted you to do this test this week so you could see how it's done and how it's interpreted. So just go through each step of this week's assignment. If you didn't already install the Jamovi modules, I have the instructions from last week. I just left them there. I don't think we're going to get into too much of the extra stuff, but I'm going to leave those there. So, like we've looked at already, our steps for preparing data before we do an analysis. So we would always want to check our data for accuracy, make sure that the data types are correct in the data set, looking for any problems, scoring instruments if we need to, looking for missing data and outliers, and statistical assumptions. And we're actually going to, again, like last week, look at some of our statistical assumptions for the chi-square tests, because there are some assumptions even though these are non-parametric. At this point, you really ought to be thinking about how you would go about doing these steps in Jamovi. What kind of descriptive statistics would you run for categorical variables? And as we learned earlier in the semester, for categorical variables, which are nominal and ordinal level of measurement, the descriptive statistics that you ought to run are frequencies and percents, and what kind of plots are the best to look at, and bar charts are probably the most appropriate type of a plot for categorical variables, because that gives you frequencies or percents for each group. What kind of descriptive statistics would you run for continuous variables? And those are interval and ratio level of measurement, and means and standard deviations are your first choice if you have parametric data or normally distributed data. And if you have skewed data or outliers, then medians and with quartiles and a range with a minimum and maximum are probably appropriate to look at. And the best plots for continuous data are histograms and box plots. So choosing a statistical test. So as I've told you before, Jamovi has a tool to help us learn how to which test to select. So we're going to take a peek at that before we go any further. So I'm going to go ahead and open Jamovi. And I'm going to open our data set. And you would want to just navigate to where you have it. This is the zip file from Field that you can download with all the data sets used in his text. So this week we're going to look at this cats.save, and I think I put a copy of it in the zip folder. But if you just download his zip file with all of his data sets, you can open it up from there also. And let's go ahead and go into, well, we can take a quick peek and see what we have here. We have one variable called training, and his example from his book, this is actually some made up data using type of training, using food as reward or using affection as reward, and whether or not you can get a cat to dance. And you have two outcomes possible, yes and no. So that's just a brief introduction. It's probably good to mention that he uses a lot of funny examples, but if you want to translate this to your variables of interest, then really the only thing you need to do is figure out the level of measurement of your variables, and that's going to help you know what kind of tests or analyses you can do. And so these are both categorical variables. They're both nominal and they're both dichotomous. There's two possible results for training and there's two possible results for dancing. So here we have two categorical variables, and we're going to go see what kind of test we can do that. So relationships prediction and group comparisons, we're going to go ahead and pick relationships, and training we're going to use as our independent variable. I'm going to put that into the variable 2/independent variable box. Dance we're going to use as our dependent variable. We're going to put that in our variable 1 dependent variable box. And you can see StatCat gives us a recommendation of a chi-square test of association. So that is good because that's what we're going to do this week. But I just want you to get used to using this if you're trying to figure out what kind of test you can do. If you want to go memorize what levels of measurement go with which test, then fantastic. That's probably the best way to go, but that takes a good bit of time. I spent plenty of time trying to do that. So I know it because I memorized a lot of it, but this is a tool that can help you if you're trying to figure it out. And there's different sheets and things online, but this is set up pretty nicely. Again, if you look at these, this page will actually take you to a web page where it describes the particular test and the null and alternative hypotheses. And I have not read through the chi-square page on this, so I don't know how well what I have in this assignment matches their descriptions or not, but that's handy to know. Let's go back to our assignment. So we did that part, you can answer the chi-square test of independence for our answer on that. So there's kind of a set of steps that you follow every time you do a statistical test. And different texts and resources may list it a little different. Some say there's 4 steps, some say there's 5 steps, some say there's 7 steps, depending how much they want to put together or break apart. But they all follow this basic type of pattern. So if you're looking at the really big picture, you're going to decide upon a research question and hypothesis. And that gets down to the point that there really are a couple kinds of hypotheses that you deal with when doing statistics. One are research hypotheses, which deal very directly with your question. So in the case of his example of getting cats to dance, he thinks that your research hypothesis might be something about cats learn to dance better with a certain type of reward, whatever that is. But that doesn't really tell us much specifically for the statistics. We're going to get into that in just a second. But that's a research hypothesis. When you come up with your research question hypotheses, then you'll need to determine the appropriate type of data to collect, what variables and what level of measurement for each one of those, and figure out what would be the appropriate statistical analysis. So some of them call that choosing the probability distribution, because different types of data follow different types of probability distribution. And in the case of chi-square tests, those follow a chi-square distribution. So when you're looking at categorical data, that's your distribution. And our test statistic is a chi-square statistic. Then once you've made those decisions, you're going to collect your data. And obviously we're not going through all those steps, but what we're picking up in this class is going to start here. It's state the null and alternative hypothesis. So this is where we're going to say what our specific null and alternative are for our specific statistical test. So in the case of our chi-square, we're going to say chi-square test of association. The null is always going to be some form of there is no difference or there is no relationship. And in the case of a chi-square test of association, we could get a little more specific and say there's no difference between observed and expected frequencies. The alternative would be that there is a difference. And so here for chi-square test of association, we'd say there is a difference between the null and alternative hypotheses, or we're saying there is a relationship between these two variables. Set the criteria for rejection, which is pretty much deciding on an alpha level. For all of our assignments, we're going to be using the basic alpha equals 0.05. Then we're going to calculate a test statistic, which is basically running your software and getting a test statistic and p-value back. And then you're going to make a decision. Are you going to reject the null or fail to reject the null? And then report your results. So we're going to follow this pattern over and over again as we do different statistical tests. And obviously the specifics are going to change, but the pattern remains the same. So I would say memorize that pattern. That will serve you well for the rest of your life with statistics. So before we get into a chi-square test of association, we're going to run a chi-square goodness of fit. And Field did not really run one of those so specifically, but I'm going to have you guys run one just so you can see it. It's not a test that I use very much. What the chi-square goodness of fit test is let you do is it lets you determine if the frequencies that you observe in a categorical variable match a a predetermined set of frequencies. So if you had two groups, maybe you're trying to decide, are the groups 50-50? Are there the same number in each group? Or say you had four groups, are there 25% in each one? Or is one group 75% of the total and a lower number in each other group? You can decide what the expected frequencies are, and that lets you test if what you actually have is the same as that or different. It's not something I use a lot, but it's a nice introduction to chi-square-tests, so we're going to run one. So I already opened my data set, but there are instructions here about how to open up the data set. What's the level of measurement for training? What's the level of measurement for dance? You guys can answer those. What's the correct descriptive statistics for training and for dance? And what are the correct plots for training and dance? You guys should know enough at this point to answer those questions. So what are the assumptions for a chi-square goodness of fit test? So one assumption is that you have one categorical variable of interest. We're going to look at training type of reinforcement. That the observations are independent. You don't want to be looking at the same individuals more than once for a chi-square goodness of fit test. You want the groups to be mutually exclusive. That means people cannot belong to both groups. They have to be in one or the other. So sometimes you do have situations where people can belong to more than one group, and then you're violating an assumption of a chi-square test, and you shouldn't run that kind of test on that kind of data. And the last assumption is the expected frequency in each group is 5 or greater. So you really can't have any groups that are less than 5, or you're violating an assumption of a chi-square goodness of fit. And Field talks about some alternatives, but we won't talk about them on this assignment. So what are the null and alternative hypotheses for a chi-square goodness of fit? So Field didn't really go over that so closely, but learning statistics with Jamovi, chapter 10.1.2, gives a nice example. And the null hypothesis is there is no difference between observed and expected frequencies, and the alternative would be there is a difference between observed and expected frequencies. So what is the criteria of rejection? I give you a couple examples here of, you don't always have to use alpha 0.05. Sometimes you might be doing a pilot test or looking for trends, some exploratory analysis. You might relax that and use an alpha of 0.1. Maybe you're doing something like a drug study, and there could be some very significant consequences for having false positives. And so you might be a little more strict and choose an alpha of 0.01. So we're gonna go ahead and stick with alpha 0.05 for these assignments. So that's what we're gonna use. Do we meet the statistical assumptions? And for this test, yes, we do. We're just looking at one variable, which is training. Are the observations independent? Yes. Are the groups mutually exclusive? Yes. They can't belong to more than one group. And expected frequency in each group is greater than 5. And yes, it is. Now we're going to calculate the chi-square goodness of fit test. So if you go into Jamovi, we're going to go into frequencies, one sample proportion tests, and we're going to pick this, and outcomes, and we're going to put training in the variable box, and you can see that we get some counts and some proportions. We're going to go ahead and click on the box for expected counts so we can see those there. And This defaults to giving us the same number in each group, but you could change these ratios and change these proportions, but we're going to leave that how it is. So we can see here that we have a chi-square statistic of 76.9. It used to be that p-values were kind of hard to calculate, so that they would use tables of things. And it looks like my pug came downstairs, so he's going to sit with me. And we have a p-value of p less than 0.001. So what would we do with that? If p is less than 0.05, then we're going to reject the null. And you always want to get a real interpretation of that and say what this means in some plain language. And we decided before that the alternative hypothesis was that there's a difference between the observed and expected frequencies. And if we take a look at that, the food as a reward, we observed 38. The expected count was 100 because there were 200 total participants. In the affection, we observed 162. The expected count was 100. And those are quite different than each other. So when we reject the null, we're basically saying that there's a difference between the observed and expected frequencies. And you can go a step further and say that using food as a reward has fewer than we expected, and using affection as a reward had more than we expected, based on were we expecting equal groups. So that kind of identifies the pattern. You always want to do that for readers also. So that's our decision. We'd reject the null. There's an interpretation you could fill out. So now we're going to move on to the more widely used chi-square test of independence or chi-square test of association. Those are pretty much independent or interchangeable terms. You'll hear both and see both all the time. So this is used to test to see if two categorical variables are related. And kind of the big difference between these two tests, besides the fact that there's two variables, is in how we derive our expected values. And in a chi-square goodness of fit test, we get to choose what the expected values are because we get to pick what proportion we're looking for, whether that's each group is the same or one group is bigger and the other ones are smaller. You get to choose, and that's what we test against. But in a chi-square test of independence, expected frequencies are calculated, and the computer will do that for us, and we'll see what they look like. So what are the assumptions for a chi-square test of independence? Field talks a little bit about that in chapter 19.5, and learning statistics with Jamovi, which the link is earlier in the assignment, does that in chapter 10.5. But we're basically looking at two categorical variables. The observations are independent. Groups are mutually exclusive. All expected frequencies have to be greater than 1. You can't have any categories where you have an expected frequency of 0. And no more than 20% of the expected frequencies are less than 5. So if you had one variable that had 2 groups and one variable that had 4 groups, that would be 8 different expected frequencies when you did the crosstabs for that. And 20% of that would be, how many is 20% of 8? Probably no more than one cell, could be less than 5. So Field talks a little about what some alternatives are if you violate some of those assumptions, but I'm not going to look at that. So just understand that's an assumption of a chi-square test of independence. So what are the null and alternative hypotheses for a chi-square test of independence? And I kind of said it succinctly that the observed frequencies are the same as expected frequencies. That's our null hypothesis. That indicates there's no relationship there. And the alternative is that observed frequencies are not equal to expected frequencies. They're different. And that would indicate there is a relationship between those two variables, where one variable affects the other one. So what is the criteria for rejection? Again, we decided we're going to stick with 0.05. So do we meet our statistical assumptions? So are we looking at two categorical variables? Yes, we do. Are the observations independent? Yes, they are. Are groups mutually exclusive? Yes, they are. All expected frequencies are greater than 1? Yes, they are in this case. And less than 20% of expected frequencies are less than 5. And we don't have any that are that low, so we do meet that assumption. Calculate the chi-square test of independence. So we're going to go to Jamovi. We're going to hit frequencies. This time we're going to go down to the contingency tables, and we're looking at independent samples. So we'll pick the chi-square test of association, they call it. We're going to put training in the columns and dance in the rows, and those are pretty much interchangeable. But if I am doing something where I'm manipulating one variable and then seeing an outcome, I like to put, oh, I think I did that backwards from what I wanted to do. I think I want to put training in the rows and dance in the columns, because I kind of like to see what the thing we're manipulating is and what the outcome is in the columns. So, like I said, it's interchangeable. You can do it the other way, but your results wouldn't match mine if you do it that way, and it's probably easier to learn when things match. Under statistics, we're getting a chi-square statistic. We're getting confidence intervals. I like to get the effect size for phi and Kramer's V. You can read in field what those mean. And in cells, we want to see our expected counts, and you can bring up percentages if you want to. One thing that is missing in Jamovi that I always look at are something called standardized residuals. In the field text in his example, you'll see that he gets those. SPSS does get those, and I find they're very useful for understanding and interpreting the results of our chi-square chi-square test of independence. So, but we can calculate them, and we'll do that in our assignment. So unfortunately, that is one thing that's missing at this time from Jamovi, but we can get around that. Okay, so what's our chi-square statistic? What's our p-value? And what's our phi? Chi-square is in this table, 25.4 with a p less than 0.001. That's definitely significant. It's our 200 participants. And if you have a 2x2 table, phi is the correct effect size to look at, 0.356. It's small bordering on medium. And Kramer's V, if you have a bigger contingency table with more than a 2x2, then it could be a 2x4 or a 3x3, something like that. Kramer's V would be the appropriate thing to report. In this case, they're the same, but if there were a bigger table, then you'll start to see a little bit of difference there. So I'd report the Kramer's V. And standardized residuals in a chi-square test are a way to see which cells are most responsible for the result that we get. We have a significant result, p less than 0.001, so we do want to look at that. And the formula for standardized residuals is the observed frequency subtract the expected frequency divided by the square root of the expected frequency. And I went ahead and pulled those numbers for you and put them in some R code, and we're going to go run that. And we have those. So what decision would we make about the null hypothesis? And we know that our p is less than 0.05, so we would reject the null. How would you interpret that? So we can see here on these standardized residuals that food as a reward and no dancing, the standardized residual is almost negative 2.8. And with any standardized score, we're always kind of looking for that magic number of 2. On z-scores, if something is much beyond 2, it becomes an outlier, and it's kind of an atypical score. So this standardized residual is negative 2.8. That means it's a good bit lower than we would expect. And when we look at food as a reward and dancing yes, we see it's positive 2.26, so that's larger than we expected. These standardized residuals are less than 2, so they're not too extreme. So really what this is telling us is that using food as a reward seems to be less effective at getting casted ants because our observed frequencies are lower than what we had expected based on just calculating them. And using food as a reward seemed to be a little more effective at getting casted ants because that observed is higher. And with those standardized residuals, we calculated those, and we could see that those scores were beyond 2. And that is going to be our interpretation, and that those standardized residuals help us kind of figure out what was going on. So there does seem to be a relationship between what type of training to use and whether or not cats dance. Reporting results field gives a nice example in his chapter 19.8.5. We're not going to write that out right here, but should you need to do a test, then follow his pattern of how he reports that result. And the rest of this is similar to other assignments. You can give some feedback and then save your RStudio file. And if we try and knit this, and that seemed to work, and you want to turn in your HTML file that gets generated for your assignment, and also save your Jamovi file. Save as. We'll hit browse, and we'll go to there we are. Users. Mine's kind of buried a little bit, but you can navigate to yours. Alright, so You can turn in your HTML file and your OMV file. And those will, there's my OMV file. Those will be your assignment for this week. All right, hope you guys have a good week. I will see you in office hours.